Consider the moment you are living in right now. It feels solid, singular, moving forward with a steady and irreversible pull. The past is fixed and finished. The future has not yet arrived. Between them, you sit at a boundary that never stops sliding forward. This experience is so ordinary that we rarely question it. Time flows. That is simply how the world works. But there is a physicist who spent much of his life refusing to accept that answer. He is one of the most decorated scientists of the modern era, a man whose mathematical work reshaped how we understand black holes, gravity, and the deep structure of space itself. His name carries weight in every serious discussion of cosmology, and near the end of a long and honored career, he proposed something that many of his colleagues found difficult to accept. He suggested that time may not have begun the way we think it did, and that it may not end the way we assume it will. His idea reaches beyond the birth of our universe and beyond its eventual death. It asks whether the beginning and the end might be connected, whether what we call the origin of everything was itself the continuation of something older. To follow his reasoning, we have to examine the nature of time, the strange orderliness of the early cosmos, and the quiet mathematics that might link one universe to the next. This is not a story of certainty. It is a story of a careful mind following the evidence to an unusual conclusion, and asking us to consider that our conception of time and the universe may be incomplete. The physicist at the center of this story is Roger Penrose, and to understand why he came to distrust our ordinary picture of time, it helps to understand the kind of thinker he has always been. He is a mathematician first, a man who sees the world through geometry and structure rather than through equations alone. Colleagues describe him as someone who thinks in pictures, who reaches conclusions by visualizing shapes and relationships before translating them into formal proof. This habit of mind matters, because the questions that would eventually consume him are not questions that yield easily to calculation. They are questions about the shape of reality itself, about why the universe is arranged the way it is rather than some other way, and about whether the arrangement we observe makes sense when examined closely. Penrose came of age in a period when physics was undergoing a quiet transformation. The general theory of relativity, developed decades earlier, had described gravity not as a force pulling objects together, but as a curvature in the fabric of space and time. Massive objects bend the space around them, and that bending is what we feel as gravity. For a long time, this theory was admired but somewhat neglected, treated as elegant mathematics with limited practical consequence. Then, in the middle of the 20th century, a new generation of physicists began to take its stranger predictions seriously. Among those predictions was the possibility that a star, having exhausted its fuel, could collapse so completely that it formed a region from which nothing could escape. Penrose became one of the people who proved that such regions were not mathematical curiosities, but genuine consequences of the theory. His work helped establish that under certain conditions, collapse leads inevitably to a point where the known laws of physics break down, a place where density becomes infinite and space and time lose their ordinary meaning. That conclusion planted a seed. If the death of a large star could produce such a breakdown, a place where the smooth fabric of space tears into something the equations cannot describe, then perhaps the birth of the universe involved something similar. The prevailing model of cosmic origins, which described the universe expanding outward from an extremely hot and dense state, seemed to point back toward a comparable breakdown at the very beginning. Run the expansion backward in time, and everything grows hotter and denser until you reach a moment where the mathematics again fails. Physicists call these breakdown points singularities, and the beginning of the universe appeared to be one of them. But here Penrose noticed something that troubled him, and this observation would occupy him for the rest of his working life. The singularity at the beginning of the universe and the singularities formed inside collapsing stars did not seem to be the same kind of thing. On the surface, they looked similar. Both were points where density soared and the equations lost their footing. Yet, when he examined their structure carefully, using the geometric intuition that came naturally to him, he found that they were profoundly different in character. The singularities produced by collapsing matter were chaotic and complex, tangled knots of curvature. The singularity at the origin of the cosmos, by contrast, appeared to have been extraordinarily smooth and ordered. It was as if the universe had begun in a state of near-perfect regularity, while the objects forming within it tended toward the opposite condition. This asymmetry may sound like a technical detail, the sort of thing that interests specialists and no one else. But Penrose recognized it as something deeper. He saw in it a clue to one of the oldest and most stubborn mysteries in all of physics, a mystery hiding in plain sight within our everyday experience. It is the mystery of why time seems to flow in only one direction. Think about the difference between the past and the future. You can remember yesterday, but you cannot remember tomorrow. A glass that falls from a table shatters on the floor, but shattered glass never gathers itself back together and leaps upward onto the table. Heat flows from a warm object to a cold one, never the reverse without help. Smoke spreads out from a fire and disperses into the air, but it never spontaneously collects itself back into a compact plume. Everywhere we look, processes run in one direction and not the other. There is a distinction between before and after that is written into the world at every scale. What makes this strange is that the underlying laws of physics, the fundamental rules that govern how particles move and interact, do not themselves distinguish between forward and backward in time. If you could watch a film of two particles colliding and bouncing apart, and someone ran that film in reverse, you would see nothing that violated the laws of physics. At the level of individual interactions, the equations work equally well in both directions. And yet, our experience of the world is overwhelmingly one-directional. Somehow, from laws that do not care about the difference between past and future, there emerges a reality in which that difference is one of the most obvious features of existence. The resolution to this puzzle, as physicists have understood it for well over a century, lies in a concept called entropy. Entropy is often described loosely as a measure of disorder, though a more careful description is that it measures the number of ways the components of a system can be arranged while still looking essentially the same from the outside. Consider a room with a small amount of gas in it. There are relatively few ways for all the gas molecules to be crowded into one corner, but there are vastly many ways for them to be spread evenly throughout the room. Because the spread-out arrangement can be achieved in so many more ways, it is overwhelmingly more likely. Left to itself, the gas will always tend toward the spread-out state, simply because that state is so much more probable. This tendency is captured in what physicists call the second law of thermodynamics, which states that in an isolated system, entropy tends to increase over time. Order gives way to disorder, not because of any force pushing it that way, but because disorder is so much more common among the possible arrangements. This law gives us the arrow of time. The reason the past differs from the future is that the past had lower entropy, and the future will have higher entropy. The glass shatters because a shattered glass represents a higher entropy, more disordered arrangement than an intact one, and there are countless ways for glass to lie broken, but very few ways for it to be whole. Heat flows from hot to cold because the even distribution of energy is more probable than the concentrated one. The direction we call forward in time is simply the direction in which entropy increases. This is one of the great insights of physics. connecting our intuitive sense of time's flow to the statistical behavior of matter. But Penrose pressed further, and this is where his particular genius reveals itself. The second law tells us that entropy increases as we move into the future. Fair enough. But this immediately raises a question that most people never think to ask. If entropy is always increasing, and has been increasing throughout the entire history of the universe, then it must have been lower in the past, and it must have been lower still further back. Follow this chain of reasoning all the way to the beginning, and you are forced to conclude that the universe must have started in a state of extraordinarily low entropy. The early cosmos must have been remarkably ordered, far more ordered than anything we see today, in order for there to have been so much room for entropy to grow over the billions of years since. This is the point that Penrose insisted his colleagues take seriously. The arrow of time, that most familiar feature of our existence, does not really originate in the second law of thermodynamics. The second law only tells us that entropy increases. It does not explain why entropy was ever low enough to increase from in the first place. The real question, the question underneath all the others, is why the universe began in such an exquisitely ordered condition. Everything about the flow of time, everything about memory and cause, and the difference between what has happened and what is yet to come, traces back to that initial orderliness. And nothing in our standard account of cosmic origins explains where that orderliness came from. Most physicists, confronting this question, treated the low entropy beginning as simply a given, an initial condition that the universe happened to have. You have to start somewhere, and this is where the universe started. But Penrose found that answer deeply unsatisfying. He had spent his career studying the geometry of singularities, and he knew that the ordered beginning was not just unlikely in some vague sense. When he tried to estimate just how special the initial state had to be, the numbers he arrived at were so extreme that they resisted comprehension. The precision required to set the universe up in such a smooth, low entropy condition was, by his reckoning, almost beyond imagining. A universe chosen at random from all the possibilities would look nothing like ours. Ours had been arranged with a fineness that cried out for explanation. And so, Penrose was left holding a question that would not let him go. The orderly beginning of the universe is the source of time's arrow, the reason the past and future feel so different, the foundation of the entire structure of cause and consequence that makes our experience coherent. Yet this orderly beginning is precisely the thing our theories do not explain. It sits at the root of everything and is itself unaccounted for. To confront that gap honestly, he realized, would require rethinking not just the beginning of the universe, but the very geometry of how order and disorder are stored in the fabric of space and time. What kind of hidden bookkeeping could allow the cosmos to begin so smooth and yet contain the seeds of all the complexity that followed? To appreciate why Penrose's later ideas provoked such strong reactions, it is worth pausing on the stature of the man proposing them. This was not a fringe figure making claims from outside the establishment. This was someone whose contribution sat at the foundation of modern gravitational physics, whose name appeared on theorems that every graduate student in the field was required to learn. When he spoke about singularities, black holes, or the structure of space and time, he was speaking about subjects he had personally helped to define. That authority is part of what made his unconventional cosmology so difficult to dismiss, and also part of what made it so uncomfortable. A less established scientist proposing the same ideas might have been ignored. Coming from Penrose, they had to be taken seriously, even by those who suspected he was mistaken. His path into physics was unusual. He trained originally as a pure mathematician, and he never fully abandoned that identity. Where many physicists reach for computation and experiment, Penrose reached for geometry and visual reasoning. He had an extraordinary ability to see mathematical structures in his mind, to manipulate shapes and spaces mentally in ways that others found difficult to follow. This gift showed itself early in his fascination with impossible figures, drawings that seem locally coherent but cannot exist as whole objects. He devised versions of these figures that were later made famous by artists, staircases that climb forever while returning to their starting point, triangles that cannot be built yet appear perfectly reasonable on paper. These playful constructions were more than curiosities. They reflected a mind attuned to the tension between what seems locally possible and what is globally consistent, a tension that would later prove central to his serious scientific work. When Penrose turned his attention to general relativity, the field was in a peculiar state. Einstein's theory had been established for decades, but its most dramatic implications remained poorly understood. The equations were notoriously difficult to solve, except in highly symmetric, idealized situations. Real stars are not perfect spheres. Real collapse is not perfectly uniform. And many physicists suspected that the extreme predictions of the theory, the singularities and the points of infinite density, were artifacts of these unrealistic assumptions. Surely, they reasoned, a more realistic and messy collapse would avoid such pathological outcomes. The matter would swirl and spin and miss the exact center, and no true singularity would form. Penrose overturned this comfortable assumption. Using methods drawn from topology and geometry, rather than from the direct solution of equations, he demonstrated that singularity formation did not depend on perfect symmetry. Once a collapsing region of space passed a certain threshold, a point of no return where the gravitational pull became strong enough to trap even light, the formation of a singularity became unavoidable. It did not matter how irregular or lopsided the collapse was. The conclusion followed from the general structure of the theory itself. This result, developed in the middle of the 1960s, transformed black holes from speculative possibilities into rigorous consequences of general relativity. It established that if the theory was correct, then singularities were real features of the universe, hidden inside collapsing stars. The significance of this work extended well beyond the study of individual stars. If singularities formed in collapse, and if the universe itself had emerged from something resembling a singularity in reverse, then the same mathematical machinery might illuminate the origin of the cosmos. This connection drew Penrose into collaboration with a younger physicist who would become one of the most famous scientists of the age, and together they extended the singularity results to the universe as a whole. Their combined work suggested that, under the accepted understanding of gravity and the observed expansion of the universe, a singularity at the beginning of time was not merely possible but required. The cosmos appeared to have emerged from a state where the known laws broke down completely. For decades, this body of work defined Penrose's reputation. It was rigorous, influential, and widely celebrated. Eventually, it would be recognized with the highest honor in the discipline, an acknowledgement that his mathematical demonstrations had permanently changed how physicists understood gravity and the fate of matter under extreme conditions. The recognition came late, many years after the original work, but it confirmed what the field had long understood. Penrose had shown that the strange predictions of general relativity were not to be explained away. They were to be confronted. Yet, even as his early work earned lasting acclaim, Penrose was never entirely content to remain within the boundaries of accepted physics. He had a restless quality, a willingness to question assumptions that most of his colleagues treated as settled. This tendency showed itself in several directions over the course of his career. He developed novel mathematical tools for describing space and time, seeking deeper structures beneath the familiar framework of relativity. He proposed patterns and tilings in pure mathematics that turned out to have unexpected connections to the physical world, describing arrangements of matter that had been thought impossible. And he ventured into territory that made many scientists distinctly uncomfortable, questioning whether the human mind could be fully explained by the same computational principles that govern ordinary machines. This last venture is worth noting, because it reveals something about his character that bears on the cosmological ideas to come. Penrose argued, in a series of controversial books and papers, that human understanding involved something that could not be captured by any computation, no matter how sophisticated. He drew on deep results in mathematical logic to suggest that the mind grasped truths in a way that no mechanical procedure could replicate, and he speculated that the explanation might lie in undiscovered physics operating at the smallest scales within the brain. Most of his colleagues in physics and in the study of the mind regarded these arguments as unpersuasive, and the specific mechanisms he proposed have not been widely accepted. But the episode illustrates a pattern. Penrose was willing to follow his reasoning into unpopular conclusions, to stake out positions that placed him at odds with mainstream opinion, and to do so not out of contrarianism, but out of a genuine conviction that certain problems demanded unconventional answers. That same willingness shaped his approach to the puzzle of time's arrow and the ordered beginning of the universe. Where others were content to accept the low entropy start as a brute fact, Penrose could not let it rest. His instinct, honed over decades of geometric reasoning, told him that such an extraordinary condition demanded an explanation, and that the explanation would not come from within the standard picture. It would require stepping outside the usual assumptions about how the universe began and what came, if anything, before it. He suspected that the answer lay in the geometry of the beginning itself, in the specific way that curvature and order were distributed at the origin. There was also a personal dimension to his persistence. Penrose had watched physics grow increasingly reliant on ideas that he found mathematically unmotivated, additions to the standard picture that were introduced to solve specific problems, but that lacked, in his view, a deeper justification. He was skeptical of certain fashionable theories that many of his colleagues embraced, particularly proposals about the earliest moments of the universe that invoked a burst of rapid expansion to smooth everything out. To Penrose, such proposals did not solve the fundamental puzzle. They merely relocated it. If the universe needed to be in a special state for rapid expansion to begin, then invoking that expansion did not explain the special state. It assumed it. The orderliness had to be accounted for at a more basic level. So the question remained, sharper than ever in his mind. The universe began in a condition of astonishing order, an order that was the ultimate source of time's forward flow and everything that depended on it. This order was not a minor detail, but the central fact requiring explanation, and it was precisely the fact that standard cosmology took for granted. To make progress, Penrose would have to characterize that order with precision. He would need to say exactly what was special about the beginning, in what specific way it differed from the disordered singularities inside black holes, and how that difference could be captured in the language of geometry. Only by pinning down the nature of the initial order could he hope to understand where it came from. And that meant looking closely at how gravity itself, the very curvature of space and time, could serve as a kind of reservoir for order and disorder in ways that ordinary matter could not. The path forward began with a closer look at what entropy really means when gravity enters the picture, because gravity changes the story in ways that are easy to overlook. In everyday examples, the low entropy state is the orderly one, and the high entropy state is the spread-out one. A drop of ink concentrated in one place has lower entropy than the same ink dispersed evenly through a glass of water. This matches our intuition. Concentration looks orderly, dispersal looks disorderly, and things naturally move from the former to the latter. But when gravity dominates, this intuition reverses in a way that is crucial to everything that follows. Consider a vast cloud of gas floating in space, spread thin and evenly across an enormous volume. By the ordinary reasoning of the ink drop, this smooth uniform distribution should represent high entropy, a state of maximum disorder, and in the absence of gravity it would. But gravity does not leave such a cloud alone. Every particle attracts every other particle, and over time these attractions pull the gas together. Regions that are slightly denser than their surroundings pull in more material, growing denser still, while emptier regions grow emptier. The smooth cloud breaks up into clumps. The clumps contract and heat up. Given enough time and enough mass, they collapse into stars, and the stars gather into galaxies, and the whole system becomes lumpy, structured, and dramatically uneven. Here is the key point. For a system dominated by gravity, the smooth uniform state is actually the low entropy state, and the clumped structured state is the high entropy state. This is exactly backward from our everyday intuition, and it is one of the reasons gravity is so peculiar among the forces of nature. When gravity is in charge, order looks like smoothness, and disorder looks like clumping. The universe increases its entropy not by spreading out but by pulling together, by forming ever more concentrated and structured objects out of what began as a featureless haze. This insight reframes the mystery of the ordered beginning. When Penrose said the early universe had extraordinarily low entropy, he did not mean it was concentrated into a tidy point. He meant something more specific and more revealing. He meant that the matter and energy of the early universe were distributed with remarkable smoothness. The evidence for this smoothness is not speculative. It is written across the sky in the form of the oldest light in existence, radiation left over from a few 100,000 years after the beginning, when the universe first became transparent. When we map this ancient light, we find that it is astonishingly uniform in every direction. The temperature is the same to a precision of a few parts in 100,000, no matter where we look. The early universe was, gravitationally speaking, about as smooth and featureless as anything could be. And that smoothness, in the presence of gravity, means the early universe was in a state of extraordinarily low entropy. It had enormous room to grow more disordered, and the way it would grow more disordered was through the clumping that gravity drives. All the structure we see around us, every star and galaxy and cluster, represents entropy that has been generated as gravity pulled the smooth beginning into an increasingly lumpy present. We are living in the middle of that process, riding the increase in entropy from a smooth past toward a clumped future. But this raised, for Penrose, an even more pointed version of his original question. Why was the beginning so smooth? Recall that the singularities inside black holes, the endpoints of gravitational collapse, are wildly disordered, tangled regions of extreme and chaotic curvature. If the beginning of the universe was also a kind of singularity, why was it the exact opposite, smooth and uniform rather than chaotic and clumped? The two situations seem symmetric in some respects. Both involve extreme conditions where the known physics breaks down. Yet one is maximally ordered and the other maximally disordered. Something must distinguish them, some principle that dictates why the initial singularity was constrained to be smooth, while the singularities of collapse are free to be as tangled as they please. To capture this distinction precisely, Penrose turned to the mathematical description of curvature in general relativity. In Einstein's theory, the curvature of space and time can be split into two parts, and this split turns out to be essential. One part describes how volumes are distorted by the matter directly present. If you imagine a small cloud of particles falling freely, this part of the curvature describes how the cloud changes in size, how it is squeezed or expanded by the matter and energy in its vicinity. The other part describes a different kind of distortion, one that changes the shape of the cloud without necessarily changing its volume. It describes stretching in one direction and squeezing in another, the tidal effects that distort a falling shape into something elongated or flattened. This second part carries the information about gravitational effects that propagate through empty space, the ripples and tides that gravity produces even where no matter is present. Penrose focused on this second part, the component that describes shape distortion and the free gravitational field. He proposed that it could serve as a measure of gravitational entropy, a way of quantifying how much disorder is stored in the gravitational field itself. When this component is zero, space is smooth and gravitationally ordered, like the early universe. When it is large, space is full of gravitational structure and tidal distortion, the kind of thing you find near a black hole or in a highly clumped distribution of matter. In this way, the geometry of space and time carries its own ledger of order and disorder, separate from the entropy of the matter within it. With this tool in hand, Penrose formulated a hypothesis about the beginning of the universe. He proposed that the initial singularity was subject to a strict constraint. At the beginning, this shape-distorting component of curvature was required to be zero, or very close to it. The universe was compelled to begin in a state where gravitational entropy was at its absolute minimum, a state of perfect gravitational smoothness. The chaotic singularities inside black holes, by contrast, were under no such constraint. They were free to accumulate enormous gravitational entropy, to become as tangled and distorted as gravitational collapse could make them. This asymmetry, this rule that applied to the beginning, but not to the endpoints of collapse, was Penrose's proposed explanation for why time has a direction at all. The beginning was special because it was gravitationally smooth, and everything since has been the slow unwinding of that special condition into ever greater gravitational disorder. This hypothesis was elegant, and it captured the essential asymmetry in a precise mathematical form. But it also had a conspicuous weakness, one that Penrose himself acknowledged. It was, at bottom, a description rather than an explanation. It told you what condition the beginning had to satisfy, but it did not tell you why. The constraint was imposed by hand, added as a rule that the universe happened to obey, without any deeper reason for why the beginning should be governed by such a rule, while other singularities were not. Penrose had succeeded in stating the mystery with far greater clarity than anyone before him. He had shown exactly what was special about the origin, and had given it a rigorous geometric meaning. But he had not yet explained where the special condition came from. He had sharpened the question without answering it. For a long time, this seemed to be as far as one could go. The low entropy beginning was a fact that could be described but not derived. Many physicists were content to leave it there, treating it as one of those foundational features of reality that simply had to be accepted. But Penrose was not content. He kept returning to the problem, turning it over, looking for some angle that others had missed. And gradually he began to consider a possibility that was, even by his standards, unconventional. What if the smoothness of the beginning was not an arbitrary initial condition at all? What if it was smooth for a reason, because of what came before it? What if the beginning of our universe was connected, through some deep principle of geometry, to the end of a previous state of things? This line of thought required a radical shift in perspective. It meant taking seriously the idea that the beginning of the universe was not truly a beginning, not an absolute origin beyond which nothing could be said, but rather a transition, a handover from one phase of existence to another. To make such an idea coherent, Penrose would need to find a way to connect the extreme conditions of the beginning to some equally extreme situation that could precede it. He would need to identify a state that could serve as the predecessor to a smooth, low entropy origin. And to do that, he first had to understand what the universe would look like, not at its beginning, but at its very end, in the most distant future imaginable. For it was there, in the cold and empty far future, that he believed the key to the smooth beginning might be hiding. The far future of the universe is a subject that observations and established physics allow us to sketch with surprising confidence, at least in its broad outlines, and it is a picture of relentless dilution and cooling. To follow Penrose's reasoning, we must first understand what gravity does over the very longest timescales, because the answer runs contrary to what the earlier discussion of clumping might suggest. Gravity pulls matter together into stars and galaxies, generating entropy as it goes. But this clumping is not the end of the story, it is a middle chapter. The ultimate fate of the matter that gravity concentrates leads somewhere unexpected, and that destination is central to everything Penrose would propose. Begin with the fate of stars. A star shines by fusing light elements into heavier ones in its core, releasing energy in the process. But no star has an unlimited supply of fuel. Eventually, the core runs out, and the star's life comes to an end. What happens next depends on the star's mass. Smaller stars swell, shed their outer layers, and settle into dense, slowly cooling embers. Larger stars end more violently, collapsing and then blowing themselves apart, leaving behind extraordinarily dense remnants. The largest collapse completely, forming the black holes whose singularities Penrose had studied. Across the universe, star formation is a finite process. The gas available to make new stars is being steadily consumed, and although the supply will last for a very long time, it will not last forever. There will come an era when the last stars form, burn through their fuel, and fade. After that, no new stars will light up. The universe will grow dark, populated only by the cooling corpses of the stars that once shone. But even this darkness is not the final state. The dead remnants of stars, the dense embers and the collapsed cores, do not last indefinitely either. Over timescales so vast that they dwarf the current age of the universe by unimaginable factors, even these objects are expected to decay or disperse. Matter itself may not be permanently stable. According to well-motivated theoretical expectations, the particles that make up ordinary matter may slowly break down over spans of time that make the current age of the cosmos seem like an instant. If this is correct, then the dead stars will eventually crumble away, their substance dissolving into radiation and lighter particles that drift apart into the growing emptiness. Meanwhile, the black holes remain, and for a long time they are the most substantial objects left. But black holes, too, are not eternal. This was one of the great discoveries associated with Penrose's famous collaborator, who showed that black holes are not perfectly black after all. Because of subtle effects arising from the quantum nature of the vacuum near their boundaries, black holes slowly radiate energy. They glow faintly, and in glowing they lose mass. This process is extraordinarily slow for large black holes, so slow as to be utterly negligible in the present universe. But it never stops. Over enormous spans of time, a black hole gradually evaporates, shrinking as it radiates, and as it shrinks it radiates faster. In the final stages it disappears in a last burst of energy. Every black hole in the universe, no matter how massive, is on this path. Given enough time, they all evaporate away, converting the matter they had swallowed into radiation, spread thinly across space. Consider what this means for the entropy of the universe. Earlier, we saw that gravity increases entropy by clumping matter together, and that black holes, being the most extreme concentrations of matter, represent enormous reservoirs of entropy. A black hole holds far more entropy than the matter that formed it ever did. In fact, black holes are the greatest single contributors to the entropy of the cosmos, vastly outweighing the entropy of all the stars and gas combined. They are the destination toward which gravitational clumping ultimately drives, the endpoints where entropy is concentrated to its highest degree. So, the formation and growth of black holes represents the universe climbing toward maximum disorder, the fulfillment of the tendency that gravity set in motion. But when black holes evaporate, something remarkable happens to this accumulated entropy. The evaporation is not a violent scattering. It is an extraordinarily gradual leak, a slow release of low-energy radiation over spans of time that beggar comprehension. As the black hole radiates, the entropy it contained is carried away in this radiation and spread out across the expanding universe. And because the universe continues to expand throughout this process, the radiation is diluted more and more, spread ever thinner across an ever-growing volume. The concentrated disorder of the black hole is transformed into the diffuse, uniform warmth of radiation dispersed through an enormous and still growing space. So the far future of the universe, following this reasoning, arrives at a very particular state. The stars have burned out and decayed, the black holes have evaporated, the matter has dissolved. What remains is radiation, spread out with tremendous uniformity across a vast and continuously expanding space, growing colder and more dilute with every passing age. The universe ends not with a clumped, structured chaos, but with a smooth, cold, featureless bath of radiation, thinning toward nothing. The lumpiness that gravity worked so hard to create is undone, because the objects that embodied that lumpiness have all decayed or evaporated away, returning their contents to a smooth distribution. This is a striking outcome, and Penrose seized upon it. "Look at what the far future looks like," he observed. "It is smooth, it is uniform. Its matter content has been almost entirely converted into radiation, and in this respect, though it is cold and enormous rather than hot and tiny, it bears a peculiar resemblance to the beginning of the universe. The beginning, too, was smooth and uniform, dominated by radiation, before gravity had a chance to clump things together. The far future returns to smoothness after gravity has finished its work and all the clumps have dissolved." Two states at opposite ends of cosmic history share this fundamental quality of gravitational smoothness. Of course, the differences seem overwhelming. The beginning was unimaginably hot, dense, and small. The far future is unimaginably cold, dilute, and vast. One is a state of extreme compression, the other of extreme dilution. It would appear that no two situations could be more different, and that any resemblance between them is superficial at best. A smooth, hot beginning and a smooth, cold ending are still separated by every measure of temperature, density, and size that we know how to apply. To connect them would seem to require ignoring the most obvious features of each, and yet Penrose noticed something that would allow him to take the resemblance seriously, something about the far future that changes how we should think about its size and temperature. In that final state, when the universe contains only radiation spread thinly across expanding space, something strange happens to the very meaning of scale. The universe in that condition may lose its ability to keep track of size at all. It may, in a sense that requires careful explanation, forget how big it is. And if scale itself becomes meaningless in the far future, then the apparent difference between the enormous cold ending and the tiny hot beginning might not be as absolute as it seems. The gulf between them might be bridgeable after all, not by shrinking one or expanding the other, but by recognizing that the distinction between large and small has quietly ceased to matter. The claim that the universe might forget its own size sounds, at first, like a contradiction in terms. Size is one of the most basic properties we assign to anything. A thing is large or small, near or far, and these seem like absolute facts about the world. To say that scale could become meaningless requires us to examine what gives scale its meaning in the first place, and here the answer turns out to be more subtle than intuition suggests. Scale is not something the universe possesses in isolation. It is something defined by comparison, by the existence of objects and processes that carry a definite size and a definite rhythm. Take those away, and the concept of scale begins to dissolve. Think about how we actually measure size and time. To say that something is a certain length, we compare it to a ruler, to some standard object with a fixed extent. To say that a certain amount of time has passed, we compare it to the ticking of a clock, to some process that repeats at a steady rate. Every measurement of distance or duration is fundamentally a comparison against a reference that has its own scale built in. A ruler works because it has a definite length. A clock works because it has a definite period. Without such references, the notions of large and small, fast and slow lose their footing. There is nothing to measure against. Now consider what provides these references in the physical universe. What gives objects a definite size, and what gives processes a definite rhythm? The answer, at the deepest level, is mass. Massive particles are the source of scale in the universe. A particle with mass has associated with it a natural length and a natural frequency, quantities determined by that mass through the fundamental relationships of physics. Mass allows a particle to serve as a kind of clock, oscillating at a rate fixed by how much mass it has. Massive matter is what allows the universe to have rulers and clocks, what allows scale to be defined and measured. The existence of massive particles is what makes it possible to say that one region is larger than another, or that one interval is longer than another. This is where the far future becomes interesting in a new way. Recall the state the universe approaches in its final era. The stars have decayed, the black holes have evaporated, and the matter has dissolved. What remains is radiation, and radiation, in its purest form, is made of particles that have no mass at all. Light itself is carried by massless particles, particles that travel at the universal speed limit and never slow down, never come to rest, never oscillate at a fixed frequency the way a massive particle does. A universe that contains only massless radiation is a universe that has lost its rulers and its clocks. There is no massive matter left to provide a reference for scale. There are no natural lengths, no natural frequencies, nothing against which to measure how big the universe is or how much time is passing. Penrose argued that in such a state, the universe genuinely loses track of scale. Not merely that scale becomes hard to measure, but that scale ceases to have physical meaning. If there is nothing in the universe that carries a definite size, then the difference between a large universe and a small one becomes empty, a distinction without content. You could stretch the entire cold, radiation-filled future by any factor you liked. Make it 1,000 times larger or 1,000,000 times smaller, and nothing physical would change, because there is nothing in it whose size would be affected by the stretching. Massless radiation does not care about scale. Its behavior depends only on angles and on the pattern of how radiation is distributed, not on absolute distances. The physics of a universe filled only with massless particles is indifferent to overall size. This is a genuinely radical claim, and it deserves to be stated carefully. Penrose is not saying that the far future universe is small. He is saying that in the far future, the question of whether the universe is large or small has no answer, because the very framework that would give the question meaning has dissolved. The universe becomes, in the relevant sense, scale-free. And a scale-free universe cannot distinguish between being enormous and being tiny, because that distinction requires a standard of measurement that no longer exists. Now the resemblance between the beginning and the end takes on a different character. The far future is smooth, dominated by radiation, and scale-free, unable to tell whether it is large or small. What about the beginning? The beginning was also smooth and radiation-dominated, but it was extremely hot, and here something parallel occurs. At sufficiently high temperatures, particles behave as though they have effectively no mass. The energy of motion so vastly exceeds the energy associated with their rest mass that the mass becomes negligible, almost irrelevant to their behavior. In the searing conditions of the early universe, matter behaved much like radiation, dominated by energy of motion rather than by rest mass. The early universe, too, was in a state where mass hardly mattered, where the natural rulers and clocks provided by massive particles were effectively absent because the mass was drowned out by the sheer intensity of motion and energy. So, both ends of cosmic history share this crucial feature. In neither state does mass play its usual role of defining scale. At the beginning, mass is overwhelmed by heat. At the end, mass has disappeared entirely into massless radiation. And in both cases, if mass is what defines scale, then both states are effectively scale-free. The beginning does not know its own size, because its constituents are too hot to carry meaningful mass. The end does not know its own size, because its constituents have no mass to begin with. The apparent gulf between the tiny hot beginning and the vast cold ending rests on a distinction, absolute size, that neither state actually possesses. This is the crack in the wall that Penrose set out to exploit. If neither the beginning nor the end has a well-defined scale, then the objection that they differ enormously in size loses its force. You cannot say the beginning is tiny and the end is vast if neither one has a definite size to compare. The temperature difference seems to remain, the beginning hot and the end cold, but temperature too is tied to scale in ways that become slippery when scale itself dissolves. Temperature is a measure of energy per particle, and energy involves frequency, and frequency involves a clock. When the clocks are gone, when scale has become meaningless, the sharp distinction between hot and cold may soften along with the distinction between large and small. What Penrose was reaching toward was a way of describing physics that deliberately throws away information about absolute scale, keeping only the features that remain meaningful when rulers and clocks are absent. He wanted a mathematical framework that treats the universe not in terms of definite sizes and durations, but in terms of the relationships that survive when size and duration lose their meaning. In such a framework, the cold and enormous far future and the hot and tiny beginning might turn out to be describable in the same terms, might even turn out to be, in the only sense that matters when scale is gone, the same kind of state. The differences that seem so overwhelming from our scale-bound perspective might vanish once we adopt a description that does not depend on scale at all. Such a framework already exists in mathematics. It is a way of describing shapes and spaces that pays attention to angles but ignores distances, that treats two figures as equivalent if one can be obtained from the other by stretching or shrinking without twisting or tearing. This branch of geometry captures exactly the features that remain meaningful when absolute size is discarded. And it was to this geometry that Penrose turned, seeking a language in which the end of one universe and the beginning of another could be spoken of as continuous, as two faces of a single, seamless transition. To understand how such a joining could work, we need to understand what it means to describe the world in terms of angles alone, setting all measures of distance aside. The geometry Penrose needed is called conformal geometry, and grasping it requires setting aside one of our most deeply held assumptions about space, the assumption that distance is fundamental. In ordinary geometry, the kind taught in school and the kind that underlies most of physics, distance is everything. The whole structure of space is built on the notion that any 2 points are separated by a definite amount, that lengths can be measured and compared, that a centimeter is a centimeter wherever you find it. This is the geometry of rulers, and it serves us well for almost every practical purpose. But it is not the only kind of geometry, and for Penrose's purposes it was precisely the wrong kind, because it insists on the very thing, absolute scale, that he wanted to discard. Conformal geometry keeps something and throws something away. What it throws away is distance. What it keeps is angle. In conformal geometry, you are not allowed to ask how far apart 2 points are, but you are allowed to ask at what angle 2 lines cross. This might seem like a strange and impoverished way to describe space, but it turns out to preserve a great deal of meaningful structure. 2 shapes are considered the same in conformal geometry if one can be transformed into the other by stretching or shrinking, uniformly or in varying degrees, as long as angles are preserved everywhere. You can inflate a shape like a balloon or compress it, and as long as you do not shear or distort the angles, conformal geometry regards it as unchanged. A helpful way to picture this is to think about maps of the world. The surface of a globe cannot be flattened onto a page without some kind of distortion, and different maps make different choices about what to preserve and what to sacrifice. Some map projections are designed specifically to preserve angles, so that the shape of a coastline or the intersection of 2 roads looks locally correct, even though sizes are wildly distorted. On such a map, regions near the poles appear enormously larger than they really are, stretched out of all proportion to their true size. A landmass near the pole might look as large as a continent when it is really quite modest. The map has sacrificed accurate size in order to preserve accurate angles. If you only cared about angles, about the local shape of things, you would find such a map perfectly faithful. You would have no way of knowing, from the angles alone, that the sizes had been distorted at all. This is the spirit of conformal geometry. It is a description of the world in which angles are truth and sizes are convention. Now apply this way of thinking to the far future of the universe. We established that in the far future, filled only with massless radiation, scale has lost its meaning. There are no rulers, no clocks, nothing to define absolute size. This is exactly the situation conformal geometry is built to describe. A universe that has forgotten its scale is a universe best described not by ordinary distance-based geometry, but by conformal geometry, which ignores scale from the outset. In the language of conformal geometry, the fact that the far future universe is enormous is simply invisible, because conformal geometry does not register size. It sees only the pattern of angles, the shape of how radiation is distributed, and to those features the overall size is irrelevant. Something remarkable happens when you describe the far future in these terms. In ordinary geometry, the far future stretches out toward infinity, growing forever larger and colder without end. It is an unbounded expanse, a future that never concludes. But in conformal geometry, which does not care about size, that infinite expanse can be treated differently, because conformal geometry allows you to shrink things freely as long as you preserve angles. The infinite far future can be compressed, conformally, into something finite. The endless stretch of cold, expanding space can be squeezed down, in the conformal description, to a definite boundary, a smooth surface that caps off the far future. What was infinite in the distance-based description becomes finite and bounded in the scale-free description. The far future acquires an edge, a clean conformal boundary where the endless expansion is gathered up into a completed surface. Penrose had actually developed the mathematical tools for this kind of description years earlier, in a different context. He had introduced techniques for representing infinite spaces as finite ones by rescaling them conformally, drawing the far reaches of space and time into a bounded diagram where the entire history and extent of a universe could be depicted on a single page. These techniques were originally created to study the behavior of radiation and gravitational fields at great distances, and they had become standard tools in the study of general relativity, but now they took on a new significance. The conformal boundary of the far future was not just a mathematical convenience. Penrose began to suspect it might be physically meaningful, a real surface where something could happen, rather than a mere diagrammatic trick. The same kind of treatment can be applied to the beginning of the universe. The beginning, too, was a state where scale had lost its meaning, where matter behaved as though massless because it was so hot. And so, the beginning, too, can be described in conformal terms, as a conformal boundary. But here, the situation is reversed. The beginning is not an infinite expanse being compressed into a finite surface. It is an extremely hot, dense state whose conformal description yields a boundary of a different sort, a smooth surface marking the start of things rather than their end. The beginning has its own conformal boundary, a clean surface where the history of the universe begins. Now, the two boundaries can be placed side by side. The far future of the universe ends, in conformal terms, in a smooth boundary surface. The beginning of the universe starts, in conformal terms, in a smooth boundary surface. Both are described by the same kind of geometry, the geometry of angles without distances, because both are states where scale has ceased to matter. And this is the moment where Penrose's audacious idea crystallizes. If the far future of one universe ends in a smooth, conformal boundary, and the beginning of a universe starts with a smooth, conformal boundary, then perhaps these two boundaries are not separate at all. Perhaps the conformal boundary at the end of one universe is the very same surface as the conformal boundary at the beginning of the next. Perhaps you can join them, matching the end of one to the beginning of another, so that the two universes share a common boundary, a seam where one becomes the other. This joining is only possible because conformal geometry has thrown away scale. In ordinary terms, matching the cold, infinite far future to the hot, dense beginning would be absurd, an attempt to equate two utterly different states. But in conformal terms, both states are simply smooth boundary surfaces, and the enormous differences of size and temperature between them have been declared irrelevant, set aside as scale-dependent features that conformal geometry does not see. What remains, once scale is discarded, is two smooth surfaces that can be stitched together edge to edge. The end of one aeon becomes the beginning of the next, not through any physical shrinking or heating, but through a change in perspective that refuses to distinguish between the large and the small, the hot and the cold, keeping only the smooth, conformal structure that both states share. The implications of this stitching are profound. It suggests that the beginning of our universe was not a beginning at all in the absolute sense, but a boundary inherited from the far future of a previous universe. It suggests that the smoothness of our beginning, the very smoothness that Penrose had spent so long trying to explain, was smooth, because it was the conformal continuation of a far future that had been smoothed out by the evaporation of its black holes and the dissolution of its matter. The mystery of the ordered beginning would then have an answer. The beginning was smooth because the ending before it was smooth, and smoothness passed across the boundary from one aeon to the next. To see how this complete picture fits together, and what it claims about the endless succession of universes, we need to assemble the full framework that Penrose built from these pieces. The complete framework that Penrose assembled from these ideas is called conformal cyclic cosmology, and it presents a picture of existence radically different from the one most of us carry in our minds. In the ordinary picture, the universe has a single beginning, unfolds through its history, and reaches some final state. and that is the whole of it. One universe, one beginning, one end. Conformal cyclic cosmology replaces this with something else entirely. It proposes that the universe passes through an endless succession of phases, each one called an aeon, with the far future of each aeon becoming the beginning of the next. There is no single beginning and no final end, only an unending chain of aeons, each seamlessly joined to its predecessor and its successor through the conformal boundaries we have been describing. Let us trace the full cycle as Penrose envisioned it. An aeon begins in a hot, smooth, radiation-dominated state, the kind of beginning our own universe appears to have had. Gravity goes to work, pulling the smooth matter into clumps, forming stars and galaxies, generating entropy as structure emerges from smoothness. The clumping intensifies. Some matter collapses into black holes, the great reservoirs of entropy, which grow by swallowing surrounding material and by merging with one another. Over immense spans of time, the aeon becomes increasingly structured, then increasingly dominated by these black holes as the ordinary matter is consumed or dispersed. The stars burn out. New star formation ceases. The aeon enters its long twilight. Then the slow decline begins in earnest. The black holes, having grown enormous, start their unimaginably gradual evaporation, radiating their mass away over spans of time that dwarf everything that came before. The matter that has not fallen into black holes decays, its particles breaking down and dissolving. One by one, over epochs of staggering length, the black holes complete their evaporation, releasing the entropy they had concentrated back into radiation spread thinly across the expanding space. The structure that gravity built is undone. The clumps dissolve. The aeon approaches its far future, a state of smooth, cold, dilute radiation, dominated by massless particles, with no massive matter left to define scale. Scale loses its meaning. The aeon reaches its conformal boundary, a smooth surface where the endless expansion is gathered up into a finite edge. And that boundary, in Penrose's proposal, is not an ending. It is a handover. The smooth conformal boundary at the far future of one aeon is identified with the smooth conformal boundary at the beginning of the next. The end of one aeon becomes, quite literally, the beginning of the following one. The smoothness of the exhausted far future passes across the boundary and becomes the smoothness of a fresh beginning. What was cold and enormous on one side of the boundary becomes hot and dense on the other, not through any physical process of heating or compression, but because the conformal joining discards the scale information that would distinguish the two. From the scale-free perspective that governs the boundary, there is no difference between the smooth cold end and the smooth hot beginning. They are the same surface, viewed from two sides. This resolves the mystery that had driven Penrose for so long. The beginning of our universe was smooth, extraordinarily smooth, in a way that standard cosmology could only accept as an unexplained initial condition. Conformal cyclic cosmology explains it. Our beginning was smooth because it inherited the smoothness of the previous aeon's far future. The far future is necessarily smooth because that is where gravitational clumping ends up after all the black holes evaporate and all the structure dissolves. So, smoothness at the beginning is not a mysterious coincidence but a guaranteed consequence of how the previous aeon ended. The low entropy beginning, the source of time's arrow, is explained by the high entropy end that preceded it, transformed across the conformal boundary into what looks, on the new side, like a low entropy start. There is a subtlety here worth dwelling on, because it touches the heart of the whole scheme. It might seem that entropy should carry over the boundary. If the far future of the previous aeon had enormous entropy, and the beginning of the next aeon has very low entropy, then where did the entropy go? How can a high-entropy state become a low-entropy state simply by crossing a boundary? Penrose's answer involves the black holes and their evaporation. The enormous entropy of an aeon is concentrated in its black holes. When those black holes evaporate, and here Penrose adopts a particular and contested position, the entropy they contained is, in a sense, removed from the accounting. The information that fell into the black holes is, on his view, genuinely lost when the black holes evaporate, not preserved and released, but actually destroyed. This is a controversial stance because many physicists believe that information cannot be destroyed even by black hole evaporation. But Penrose argues that it can be, and that this loss is essential to how conformal cyclic cosmology works. The evaporation of black holes acts as a kind of entropy reset, removing the disorder that had accumulated and allowing the far future to be, in the relevant sense, smooth and low in the gravitational entropy that matters for the next beginning. This is one of the boldest and most disputed features of the whole framework. It requires that black hole evaporation destroy information, that the entropy locked in black holes be truly eliminated rather than merely transformed. It also requires that the degrees of freedom associated with the lost information be removed from the count so that the far future, despite its long and violent history, arrives at the boundary in a state fit to become a smooth new beginning. Penrose accepts these requirements as consequences of taking the framework seriously. Others regard them as reasons to doubt it, but the internal logic is coherent. If black holes destroy the entropy they concentrate, then the far future can be smooth. And if the far future is smooth, it can become a smooth beginning, and the arrow of time can be explained. There is also the question of what physically happens at the boundary to launch the new aeon. In our own beginning, the universe was not merely smooth, but full of energy, hot and dense, seething with the matter that would become stars and galaxies. Where does this energy come from if the previous aeon ended in cold, dilute radiation? Penrose proposes that the transition across the boundary involves the appearance of new matter, that the crossing itself is associated with a process that populates the new aeon with fresh material. He connects this to the idea that mass itself may fade away in the extreme far future and be reborn at the beginning, that the massive particles which define scale gradually lose their mass toward the end of an aeon and regain it at the start of the next. These are speculative elements, extensions of the framework designed to make the transition physically complete, and they remain among the least developed parts of the proposal. What makes conformal cyclic cosmology more than pure speculation, however, and what distinguishes it from many other imaginative ideas about cosmic origins, is that Penrose insisted it could be tested. A framework that merely told an elegant story about endless aeons, with no way to check it against observation, would be of limited scientific value. But Penrose argued that the previous aeon should have left traces, marks imprinted on our own universe by events that occurred before our beginning. If the aeon before ours contained violent events that sent powerful disturbances rippling toward the conformal boundary, then those disturbances might have crossed into our aeon and left detectable signatures in the oldest light we can observe. The framework, in other words, made predictions. And if those predictions could be found in the sky, conformal cyclic cosmology would move from the realm of mathematical possibility toward the realm of tested science. The question was what exactly to look for and where. The specific signature Penrose set out to find has to do with the most violent events an aeon can produce, the collisions of its largest black holes. Over the enormous history of an aeon, black holes do not merely sit in isolation. They gather at the centers of galaxies, growing to tremendous masses, and when galaxies merge, their central black holes eventually spiral together and collide. Such a collision releases a staggering amount of energy, most of it in the form of gravitational waves, ripples in the fabric of space and time that spread outward across the universe. In our own aeon, we have recently developed the ability to detect such ripples directly, confirming that these collisions occur and that they radiate energy in the way the theory predicts. Penrose reasoned that in the previous aeon, similar collisions would have occurred, and that the gravitational energy they released would have propagated all the way to that aeon's conformal boundary. Here is where the framework makes a concrete prediction. When a burst of gravitational energy from a black hole collision reaches the conformal boundary and crosses into the next aeon, it should, according to Penrose, leave an imprint. As the disturbance passes through the boundary and into the new universe, it would appear in the early stages of that new aeon as a roughly circular feature, a ring-like pattern spreading outward from the point where the energy entered. And because we can observe the earliest light of our own aeon, the ancient radiation left over from shortly after our beginning, we might be able to see these circular features imprinted upon it. They would be faint, subtle deviations in the temperature of the oldest light, arranged in concentric circles, marking the places where gravitational energy from the previous aeon had crossed the boundary into ours. Penrose gave these predicted features a name. He called them Hawking Points, in honor of his late collaborator, because they would represent the final evaporation and the accumulated gravitational signature of black holes from the previous aeon, the black holes whose evaporation his collaborator had first described. A Hawking point would be a small region in the ancient light where the signature of an entire previous supermassive black hole, its whole history of accretion and collision and eventual evaporation, had been concentrated and stamped onto the beginning of our aeon. If such points existed, they would be direct evidence of events that occurred before our universe began, messages carried across the boundary from a world that preceded ours. The ancient light in which these features would appear is the radiation released a few 100,000 years after our beginning, when the universe first cooled enough to become transparent. Before that moment, the universe was an opaque, glowing fog, and light could not travel freely. When it cleared, the light that was set loose has been traveling ever since, stretched and cooled by the expansion of the universe until it now pervades all of space as a faint bath of microwave radiation. This radiation is the oldest thing we can see, a snapshot of the universe as it was in its infancy. Detailed maps of this radiation have been made by a series of increasingly sensitive instruments, revealing its temperature across the entire sky to remarkable precision. It is in these maps that Penrose and his collaborators went looking for the circular signatures of the previous aeon, and they reported finding them. Analyzing the maps of the ancient light, Penrose and several colleagues identified regions that they interpreted as Hawking points, small patches with a particular pattern of temperature variation, arranged in the concentric structure the framework predicted. They pointed to specific locations in the sky where, they argued, the signature of a previous aeon's black hole was visible. To Penrose, these findings were powerful support for his framework. Here were the very features his theory had predicted, appearing in the data, marking the crossing points where energy from before our beginning had entered our universe. If confirmed, they would be nothing less than observations of a previous universe, a glimpse across the boundary that conformal cyclic cosmology proposed. But this is where the story becomes genuinely contested, and where the difference between a bold hypothesis and an accepted theory becomes stark. The claim to have detected signatures of a previous aeon was met with intense skepticism, and the analysis was challenged on several grounds. The central difficulty in this kind of work is the problem of distinguishing a real signal from a chance pattern. The maps of the ancient light contain a great deal of random variation, small fluctuations in temperature that arise naturally from the physics of the early universe. In any such field of random fluctuations, patterns will appear by chance. Circular arrangements, concentric structures, patches that seem to stand out, all of these can occur simply as statistical accidents, the way faces seem to appear in clouds or shapes in random noise. The question is whether the features Penrose identified are genuinely more common or more pronounced than what pure chance would produce. Critics argued that they were not. Several independent groups analyzed the same maps and concluded that the features Penrose pointed to were consistent with random fluctuations, that there was no statistically significant excess of circular patterns beyond what would be expected by chance. They constructed simulated skies, universes with no Hawking points and only ordinary random variation, and found that such simulated skies contained just as many apparent circular features as the real one. If random simulations produce the same patterns as the real data, then the patterns cannot be taken as evidence of anything beyond randomness. This was the crux of the objection. The signal Penrose saw was, according to his critics, indistinguishable from noise. Penrose and his collaborators pushed back, refining their analysis and arguing that they had accounted for these objections, that the features they identified were more significant than the critics allowed. The debate continued through successive rounds of analysis and counter-analysis, with each side defending its statistical methods and questioning the others. This kind of dispute is not unusual in science when a claimed signal sits close to the threshold of detectability. It becomes a technical argument about statistics, about how to model the background of random fluctuations, about what counts as a significant deviation, and about how to avoid fooling oneself into seeing patterns that are not really there. Such disputes are often difficult to resolve definitively, because they turn on subtle questions of method rather than on any single clear observation. The situation, then, is unsettled. Penrose maintains that the ancient light bears the marks of a previous aeon, that the Hawking points are real, and that they support his framework. Many other cosmologists remain unconvinced, holding that the claimed features are statistical artifacts, and that no genuine signal has been established. Neither side has produced evidence decisive enough to end the disagreement. It remains an open question, a hypothesis with some claimed observational support that has not been widely accepted and has been seriously challenged. This is a very different situation from Penrose's early work on singularities, which was rigorous mathematics that the field came to accept as correct. Conformal cyclic cosmology is speculative physics, and its central observational claim is disputed. But the dispute over Hawking points is only one part of the broader skepticism that conformal cyclic cosmology has encountered. Even setting aside the question of whether the predicted signatures have been found, many physicists have deeper reservations about the framework itself, about its assumptions and its internal requirements. To understand where conformal cyclic cosmology stands in the landscape of modern physics, we need to examine these more fundamental objections, the reasons that many careful scientists regard the whole framework with doubt, even before any question of observation arises. The objections that thoughtful physicists raise against conformal cyclic cosmology are worth taking seriously, because they come not from hostility to bold ideas but from a careful accounting of what the framework requires, and whether those requirements can be justified. The first and perhaps most significant objection concerns the treatment of mass. Recall that the entire scheme depends on the far future being scale-free, and that scale is defined by mass. For the far future to lose its scale completely, all the massive particles must be gone, leaving only massless radiation. But this raises an immediate difficulty. Not all massive particles are known to decay. Some particles, according to our current understanding, are stable. They do not break down over time. The lightest particles that carry mass and electric charge, for instance, have no lighter particle they could decay into while respecting the conservation laws that govern such processes. As far as we know, they last forever. If even a small population of stable massive particles survives into the far future, then the universe never truly becomes scale-free. Those surviving particles retain their mass, and their mass continues to define a scale, and the conformal boundary that the whole framework depends on cannot form cleanly. Penrose is aware of this problem, and his response is to propose that mass itself is not permanent, that even the particles we currently believe to be stable will eventually lose their mass in the extreme far future. But this is a speculative assumption with no established basis in known physics. It amounts to requiring that the universe behave in a way we have no independent reason to expect, purely because the framework needs it to. Critics regard this as a significant weakness, an assumption introduced to save the theory rather than one motivated by evidence. A related objection concerns the fate of information in black holes. As we discussed, conformal cyclic cosmology requires that black hole evaporation destroy information, eliminating the entropy that black holes concentrate so that the far future can arrive at the boundary in a suitably smooth state. But the question of what happens to information in black holes is one of the deepest unresolved problems in theoretical physics, and the prevailing view among many physicists is the opposite of what Penrose requires. Much of the theoretical work of recent decades has pointed toward the conclusion that information is preserved, that it is somehow encoded in the radiation a black hole emits as it evaporates, and that nothing is truly lost. If this prevailing view is correct, then the entropy of black holes is not destroyed, but carried away in their radiation, and the far future does not get the clean entropy reset that conformal cyclic cosmology needs. Penrose stakes out the minority position, insisting that information is destroyed, and while this position is not impossible, it places his framework in tension with a large body of theoretical work that points the other way. A third objection is more general and perhaps more philosophical, though it carries real scientific weight. Conformal cyclic cosmology introduces a substantial amount of new structure, new assumptions, and new required behaviors in order to explain a single fact: the smoothness of the beginning. It asks us to accept that mass fades away, that information is destroyed, that a specific kind of conformal matching occurs at the boundary between aeons, and that new matter appears at the transition. Each of these is a significant claim, and together they represent a considerable theoretical investment. The question that many physicists ask is whether all of this machinery is justified by what it buys. The smoothness of the beginning is indeed a genuine puzzle, but there are other approaches to it, and the dominant approach in mainstream cosmology takes a very different route. That dominant approach involves the idea of a very brief period of extremely rapid expansion in the earliest moments of the universe, a burst of growth that would have stretched any initial irregularities smooth, like the wrinkles in a balloon disappearing as it inflates. This idea has become the standard explanation for the smoothness and uniformity of the early universe, and it has other successes to its credit as well, making predictions about the pattern of tiny variations in the ancient light that have been confirmed by observation. For most cosmologists, this rapid early expansion provides a satisfactory account of why the beginning looks the way it does, and it does so within the framework of a single universe with a single beginning, without requiring endless aeons or the destruction of mass and information. Penrose, notably, is a sharp critic of this standard approach. He argues that it does not actually solve the fundamental puzzle he identified. The rapid expansion, he contends, requires its own special initial conditions to get started, and so it does not explain the low entropy beginning but merely assumes a different, special beginning of its own. He regards the standard approach as mathematically unmotivated and as papering over the deep problem rather than resolving it. This is a genuine disagreement about what counts as an explanation, and it runs deep. Penrose believes that the low entropy of the beginning demands a fundamentally different kind of account, one that reaches beyond the single universe, while most of his colleagues believe that the standard approach, whatever its imperfections, is adequate and better supported. The disagreement is not merely technical. It reflects different judgments about which problems are most pressing and which kinds of solutions are acceptable. There is also the matter of how much the framework has been developed and worked out in full detail. Conformal cyclic cosmology remains, in important respects, a sketch rather than a complete theory. The precise mechanism by which matter appears at the boundary, the detailed physics of how mass fades and returns, the exact way the conformal matching is to be implemented, these remain incompletely specified. A mature physical theory provides detailed, quantitative predictions and a clear account of its mechanisms. Conformal cyclic cosmology, by contrast, offers a compelling geometric picture with a number of gaps yet to be filled. This is not necessarily fatal. Many important theories began as incomplete sketches, but it means the framework is not yet in a position to be judged as a finished product, and it remains vulnerable to the possibility that the gaps, when examined closely, will prove difficult to fill in a consistent way. It would be easy, surveying these objections, to conclude that conformal cyclic cosmology is simply wrong, a beautiful idea that does not survive scrutiny. But that conclusion would be too hasty, and it would miss what is valuable about the framework, even if it should turn out to be mistaken. Penrose has done something that few others attempted. He identified with unusual clarity a genuine and profound puzzle: the extraordinary orderliness of the beginning and its connection to the arrow of time. He refused to accept it as a brute fact, and he constructed a serious, mathematically grounded proposal for explaining it. He connected the deepest properties of the beginning to the deepest properties of the far future, drawing a line across the entire history of the universe and suggesting that the two ends might meet. And crucially, he made his framework answerable to observation, proposing specific signatures that could be sought in the sky rather than retreating into untestable speculation. Whether or not the specific claims survive, this is science operating as it should, in the sense that a bold hypothesis has been advanced, made precise enough to be criticized and tested, and subjected to exactly the kind of scrutiny that separates lasting ideas from passing ones. The skepticism that conformal cyclic cosmology has encountered is not a sign that the enterprise has failed. It is a sign that the framework has been taken seriously enough to be examined rigorously. Ideas that cannot be criticized are not scientific. Conformal cyclic cosmology can be criticized, and it has been, and that fact places it within the domain of genuine science, even as its ultimate fate remains uncertain. What remains is to consider what it would mean for our understanding of time and our place in the universe if an idea like this one should turn out to be true. Step back from the technical disputes for a moment and consider what conformal cyclic cosmology asks us to imagine about our place in the sweep of existence. In the ordinary picture, our universe is a singular event, bounded by a beginning before which there was nothing, and heading toward an end after which there will be nothing of consequence. We occupy a brief interval of light and structure between two voids. This picture has a certain stark grandeur, but it also leaves the deepest questions unanswered. Why did the universe begin? Why did it begin in the particular ordered state that gave rise to time's forward flow? What, if anything, lies beyond its beginning and its end? The ordinary picture tends to treat these as questions that cannot be asked, boundaries beyond which inquiry simply stops. Conformal cyclic cosmology refuses to stop at those boundaries. It proposes that the beginning of our universe was not an absolute origin, but a transition, a handover from a previous aeon that lived and died before ours began. It proposes that our own far future, unimaginably distant, cold, and empty as it will become, is not a final end, but a threshold, a smooth surface that will become the beginning of another aeon, another universe with its own stars and galaxies and perhaps its own observers, looking back toward their beginning and wondering what came before. In this picture, existence has no single beginning and no final end. It is an endless succession, each aeon complete in itself yet joined to those before and after, a chain of universes stretching without limit in both directions. This is a genuinely different way of thinking about time. In the ordinary picture, time is bounded. It starts at the beginning, and it is a meaningful question to ask what the universe was like at its earliest moment, but there is no meaningful before. Conformal cyclic cosmology dissolves this boundary. There is always a before and always an after, because every beginning is also an ending and every ending is also a beginning. Time does not start and it does not stop. It flows through an unending sequence of aeons, each one experiencing its own arrow, its own progression from ordered beginning to disordered end, its own version of the very asymmetry that Penrose set out to explain. The arrow of time within each aeon is real and definite, but the sequence of aeons has no arrow, no privileged direction, no first member and no last. There is something in this that speaks to an old intuition, one that appears in many human traditions of thought, the intuition that time might be cyclical rather than linear, that endings and beginnings might be connected, that the cosmos might renew itself endlessly rather than running down once and stopping. Penrose did not arrive at his framework through any such tradition. He arrived at it through geometry, through the careful analysis of entropy and curvature, and the mathematics of scale-free spaces. But the picture he arrived at resonates with that ancient intuition in a way that is difficult to ignore. It is a scientific version of eternal return, built not on myth or metaphor but on the properties of massless radiation and the behavior of conformal boundaries. Whether or not it is correct, it demonstrates that the idea of a cyclic cosmos, endlessly renewing, is not incompatible with rigorous physics. It can be formulated precisely, made to yield predictions, and tested against observation. Consider also what the framework suggests about the far future and about the ultimate fate of everything that exists within an aeon. In the ordinary picture, the far future is a kind of tragedy, a slow dissolution into cold and darkness, the heat death of the universe in which all structure decays and all activity ceases and nothing meaningful can ever happen again. This is often regarded as the bleakest of all cosmic prospects, an eternity of featureless cold with no possibility of renewal. Conformal cyclic cosmology transforms this prospect entirely. The cold, empty far future is not the end of the story. It is precisely the condition required for a new beginning. The very smoothness and emptiness that seem so desolate are what allow the far future to become the fertile, ordered start of a new aeon. What looked like final death is revealed, in this framework, to be the necessary preparation for new birth. The heat death is not an ending, but a doorway. There is a further subtlety worth drawing out. In the far future, when scale has lost its meaning and the universe has become a bath of massless radiation, there would be no one and nothing to experience the passage of the enormous spans of time involved. Without massive matter, without clocks, without any structure to register duration, the vast epochs of the far future would pass without being marked by anything. And from the scale-free perspective that governs the conformal boundary, those vast epochs are, in the only sense that matters, no time at all. The transition from the exhausted end of one aeon to the fresh beginning of the next would be, in a sense, immediate, because the framework that would allow us to call it long or short has dissolved. The unimaginable duration of the far future and the instant of the new beginning become, at the boundary, indistinguishable. There is a strange economy in this, a sense in which the longest imaginable wait and no wait at all amount to the same thing when there is nothing left to do the waiting. What should we make of all this? It is important to hold two things in mind at once. Conformal cyclic cosmology is not established science. It rests on assumptions that many physicists doubt. Its central observational claim is disputed, and it competes with a standard approach that most cosmologists find more persuasive. It may well be wrong. A careful, honest assessment must acknowledge that the weight of current opinion does not favor it, and that the specific evidence Penrose has offered has not convinced the broader community. To present it as confirmed truth would be a distortion. It is a speculative framework, the product of one remarkable mind following a line of reasoning to an unconventional destination, and it awaits a verdict that has not yet arrived and may never arrive in a form that settles the matter cleanly. And yet, the value of the enterprise does not depend entirely on whether it is ultimately vindicated. Penrose took the most familiar feature of our existence, the flow of time from past to future, and traced it back to its deepest root in the ordered beginning of the universe. He refused to accept that root as an unexplained given, and he had the boldness to propose that the beginning was connected to an end, that the universe might be far larger in time than we ordinarily suppose, extending endlessly in both directions through a succession of aeons. He showed that such an idea could be made mathematically precise and could be brought into contact with observation. Even if the specific framework does not survive, the questions he sharpened remain, and they are among the most profound that physics can ask. Why does time flow? Why did the universe begin in such an extraordinary state of order? Is our universe all there is, or is it one episode in something larger? These questions do not have settled answers. They mark the edge of what we understand, the place where established knowledge gives way to careful speculation. Penrose spent his life at that edge, first proving rigorous theorems that reshaped our understanding of gravity and black holes, and later venturing into more uncertain territory, following his geometric intuition toward a vision of endless cosmic renewal. Whether that vision is a true description of reality or a beautiful idea that will eventually be set aside, it stands as a reminder that our conception of time and the universe is not fixed, that the boundaries we take for granted may be more porous than they appear, and that the deepest features of existence, the ones we rarely think to question, may hold mysteries we have only begun to explore. The beginning we call the origin of everything may itself have had a before, and the end we imagine as final may itself become another beginning, and time, which seems to carry us in one direction toward an ultimate conclusion, may in truth have neither a first moment nor a last.